Hello my dear students, welcome back to Aditya Tutorials. I'm Rahul and now in this video I'm going to discuss liquid solutions. In many of my videos I was explained that what is liquid solution. Liquid solutions contain two components, that is solvent and solute. And in the liquid solution the solvent is always liquid, whereas solute may be a gas or maybe liquid, or it may be solid. It means that you can add gas in the liquid, liquid in the liquid, and solid in the liquid in such a way that it should form a homogeneous mixture, that is solution. Now we're going to discuss here about the vapor pressure. Vapor pressure of liquid in liquid. This is the first part we are discussing here. Vapor pressure of liquid in liquid. It means that there are two components. The one liquid is a solvent. The another one acts as a solute. Means one liquid present in a smaller quantity, the other liquid present in a larger quantity. Now let's understand taking an example. So this is a container, and in this container we have two liquids. And now in these two liquids, I will mention it liquid number 1, or I will name it as liquid A. I will take another liquid here. And name of this liquid I will take here as liquid B. We have to think about that these liquids should be volatile liquids. These are volatile liquids. The meaning of volatile liquids, it means that these liquids at the room temperature can easily get evaporates and converts into vapors. Assume that some of the liquid molecules A present in the vapor phase. Along with that, the liquid B also present in the vapor phase. And now these vapor phase liquids colliding with themselves, and also they are colliding with wall of the container, and also they are colliding with the surface and producing here a term called as vapor pressure. The vapor pressure of any liquid depends on many factors. But in the 1886, a French chemist, Raoult, gave a quantitative relationship between the partial pressure and the mole fraction of volatile component. According to the statement, he explaining that the partial pressure of any liquid is equals to partial pressure of the same component in its purest form multiplied by its concentration in the solution. For example, if I take here the B as a solute, B is solute. Now in this case, in another container, I will take only B liquid. Okay, in the B liquid, here it is. So now only here B molecules are there, and these B molecules evaporates and converts into vapors. And now these vapors are colliding with themselves and the wall of the container. And when these collide with the wall of container and with the surface, they produce a pressure. And that pressure is known as vapor pressure. But in this case, the vapor pressure is only of B liquid. It is about only B. So therefore, the vapor pressure of B is given as P naught of B. It means that it is a vapor pressure of purest form of B. Therefore, here P naught A is the purest form of the vapor pressure, or the vapor pressure of pure liquid. In this case, I'm going to write the equation P of B, that is equal to P naught of B and mole fraction of B. So this is the equation which gives that the individual partial pressure present in the mixture of two vapors. For example, in this container there are two vapors are there, the vapor of liquid A and vapor of liquid B. But we have to calculate the vapor pressure of only B liquid. So therefore, we have to go through the Raoult's law. According to the Raoult's law, the partial pressure of any gas or any vapor of the liquid is directly proportional to or is equal to, this is the vapor pressure of the pure liquid multiplied by concentration of the liquid in the solution. Okay, so now here it is given, this is the partial pressure of B multiplied by partial pressure of the pure B, that's the vapor pressure of B, the pure B, and multiplied by mole fraction. In this, how much amount of B liquid molecules concentration is present in this solution. And by that we get here the partial pressure of individual gases. Now assume that total pressure we want here, the total pressure of both the liquids we want. Therefore, I will take here the total pressure, that is a P total, is given by the partial pressure of A, that is a P of A, plus partial pressure of B. But we know that the partial pressure of B is given by this equation. Like that, we can write the partial pressure of A in the same way. So therefore, I'm going to write here the partial pressure of A is given by P naught of A into mole fraction of A, plus we're going to add here the partial pressure of B that is given by with this equation that we have here, P naught B into mole fraction of B. The total pressure of the any gases or the vapors is given by the sum of partial pressures of A and partial pressures of B. It means that the partial pressures of individual gases, when you add, you will get the total pressure of that system. In this case, we taken here two liquids when they evaporate and forming two types of vapors, and we have to calculate the partial pressure of A and B. But come to this point, it is the equation. So this is the equation is nothing from the Raoult's law, and this one, that the P total, is taken from the Dalton's law. We know that here the mole fraction is given by XB plus XA is equal to 1. Now I will take here XB as XP is equal to, it becomes 1 minus XA. This value should be substituted in the above equation. Take this is equation number 1 and this is as equation number 2. From equation from equation 1 and 2, we have P total is equal to, here I have P naught of A into X A or mole fraction of A, plus we have here P naught of B, but XB can be written in terms of A. Therefore, I'm going to write here in the bracket 1 minus XA, that is mole fraction of A. Now we'll simplify this. We'll get here P total is equal to, this remains as it is, P naught A into mole fraction of A, plus I will take this P naught B inside. So it becomes P naught B minus P naught B into mole fraction of A. You can check here these two terms. In these two terms, mole fraction of A is common, and for that I write here P naught A XA minus P naught B into XA plus P naught B. Now we'll take XA, that is mole fraction of A, as a constant, and it is taken out. Mole fraction of A is common, we taken out. We get here P naught of A minus P naught of B plus P naught of B. Okay, now in this case, we got here the total vapor pressure is directly proportional to mole fraction of component A or the B. Since here that is a P naught A and P naught B are constants for particular liquids. You remember that this P naught A and P naught B are constants for particular liquids. At particular temperature. This relationship can be expressed with the help of a diagram that we'll see now. Now we have to represent the total vapor pressure of solution in a graphical mode, and for that I will take a graphical lines. This I am going to take vapor pressure indicated by P. On the other side, I will take here, it is mole fraction. Now, I will take the mole fraction of A here, that is mole fraction of A. And in this case, it is initial point that is 0, and along the line it will go on increases. We know that in any component, the sum of mole fraction is always equals to 1. And for that, assume that there is the purest form of A and its mole fraction is always towards 1. So here, mole fraction of A is equal to 0, and the maximum amount of mole fraction will be here. Mole fraction of A is equal to 1. Now assume that when the mole fraction of A is 0, the vapor pressure of the liquid is also 0. As the mole fraction increases along the line, the vapor pressure linearly increases, like here. Like this, the mole fraction of the liquid increases along the straight line here. We'll do the same for the mole fraction of B. For the mole fraction of B, on the other side of the line, I will take a vapor pressure. That is also indicated by P. So as we know that the sum of the mole fractions is always equals to 1. If here the mole fraction of A is 0, it means that in that mixture, the mole fraction of B is equals to 1. Like here, when the mole fraction of A is equals to 1, the sum of the two components, the mole fraction of A and mole fraction of B, are equals to 1. Always it is unity. And in this case, when the mole fraction of A is equal to 1, in that case, the mole fraction of B is equal to 0. Now assume that as the mole fraction of B in the solution increases, at the same time, the mole fraction of A should be decreases. Therefore, at the initially, when the mole fraction of B is 0, the mole fraction of B is 0. In that case, the vapor pressure of B is also 0. Okay, and for that, I'm going to write here, as the mole fraction of B increases towards the 1, mole fraction of B, when increases towards the 1, the vapor pressure is also increases in this direction. And reaches to a maximum when the mole fraction of B is equal to 1. The sum of these two mole fractions is always equals to 1. And therefore, the vapor pressure also we can sum up. And first of all, I'm going to write some of the points here. The first, this one indicate the mole fraction of or partial pressure. This is a partial pressure from the mole fraction of A or the A component. So therefore, I'm going to write here partial pressure of B. This is partial pressure of A. This is partial pressure of A. Like that, I'm going to write here, this is a partial pressure of B. Now we want the total pressure of the system. So for that, I have to connect these 2 points. This is the P total. And it is given by partial pressure of A and plus partial pressure of B. This is the total pressure of the solution. Hope you understood this. We'll move to the next part. That is, when the mole fraction of A is equal to 1, in that case, the partial pressure of A is equals to the partial pressure, that is P naught into XA, that's mole fraction of A. But here the mole fraction of A is given as 1. Therefore, the partial pressure of A is equal to the partial pressure at its purest form. Similarly, when a mole fraction of A is equal to 0, in that case, partial pressure of A is equal to partial pressure of A in its purest form. So here also I'm going to write A multiplied by 0. You will get here 0. When the mole fraction of A is 0, the partial pressure of A is also 0. It is obvious that if the container do not contain the A component, how can be a partial pressure for the A? In the plot, PA against, that is partial pressure of A against mole fraction of A, should be a straight line passing through a P naught. When, that is, mole fraction of A is equals to 1. And O, when mole fraction of A is equal to 0. So it means that when a straight line is drawn here, the straight line is passing through a 0. 0 when the mole fraction of A is equal to 0. This point is therefore, the plot of partial pressure of A, that's here, should be a straight line passing through P naught A when mole fraction of A is equal to 1. This part I will consider as P naught A when the partial pressure of A is equal to 1 and passes through a 0 when the mole fraction of A is equal to 0. Similarly, the plot of partial pressure of B against mole fraction of B, you will find that there is a straight line, and that straight line passes through P naught B when the mole fraction of B is equal to 1 and passes through a 0 or the origin when PB, that is mole fraction of B, is equal to 0. And therefore, we can conclude few points here. That is, partial pressure, when you add it up, you will get a total pressure. Therefore, P total is equal to partial pressure of A plus partial pressure of B. Or else we get here partial pressure of pure component of A multiplied by mole fraction of A plus partial pressure of pure component B multiplied by mole fraction of B. The total vapor pressure of a solution obtained by joining the two lines here. That is, P total is equal to P of A plus P of B. The composition of vapor phase. This is very interesting. This is the next part. The composition of vapor phase. Assume that there is a container, and in this container we are taking two liquids. The mole fraction of the liquid, one is given by Y of A, the other one is given by Y of B. The total mole fraction of, or sum of the mole fraction of these two components is equal to 1. Now, here there is a boundary. Above that, there are some gas molecules of B and some gas molecules of A in different compositions. But we want here the vapor phase composition in vapor phase. And this calculation is done when there is an equilibrium is established. At equilibrium. Only when the equilibrium is reached, we can able to calculate the composition of the vapor in the vapor phase. So that can be given by the partial pressure of A, that is multiplied by mole fraction of A multiplied by total pressure. P is here called as total pressure. If here I have PB, partial pressure B is equal to YB into total pressure P. Therefore, when we get here, P total is equal to P of A plus P of B, because P total is equal to, if I add the values of partial pressure of A and B, we get here Y of A into P plus Y of B into P. In this case, the P is a constant. If you take it out, you will get Y of A plus Y of B. And we know that the sum of all the components or sum of all the mole fraction components is always equals to unity. And therefore, it becomes P into 1, or that is equal to P, that is the total pressure. So this is holds good. Let's solve one particular problem on this concept. So here is a question given, students. Vapor pressure of chloroform and chloromethane are 200 mm and 415 mm of Hg. Calculate vapor pressure of solution obtained by mixing 25.5 gram of chloroform and 40 gram of dichloromethane at 298 Kelvin. And for this, I need here molecular mass of chloroform. Molecular mass of chloroform, that is CHCl3, that is equal to 119.5 grams per mole. I hope you know that how to calculate the molecular mass of any molecule. And a molecular mass of, that is dichloromethane, that is CH2Cl2, is equal to 85.0 gram per mole. Okay students, this should be per mole. Now let's see the number of moles of chloroform, that is number of moles of CHCl3, that is given by given weight, that is here, divided by molecular mass. Given weight is 25.5, and that should be divided by molecular mass, that is 109.5, and we get the answer here, that is 0.2134. And similarly, the number of moles of dichloromethane, it is N CH2Cl2, that is equal to, given weight of dichloromethane is 40 gram, here I going to write 40 gram, divided by molecular mass of dichloromethane, that is 85, and we get the answer here, that is 0.4706. The total number of moles we have to calculate. Total moles is equal to, we have to sum up these 2 points. Let's see what we get here, that is 0.684 moles. Now mole fraction we have to calculate. Mole fraction of chloroform, that is CHCl3, is equal to number of moles of CHCl3, that is chloroform, divided by number of moles of chloroform, that is CHCl3, plus we have here number of moles of dichloromethane, that is CH2Cl2. This is the total number of moles, and therefore here I am going to substitute the value that we calculated here, that is 0.2134 divided by, this is the total number of molecules or moles, that we have calculated here, that is 0.684, and by that I get here the answer. This is 0.312. Let's see the same calculation for the dichloromethane, that is CH2Cl2. In that case, the number of moles of CH2Cl2 divided by total number of moles, that is number of moles of CH, Cl3 plus number of moles of CH2Cl2, and we get the answers here, that is, here we have this mole is 0.4706 and divided by total number of moles, this is 0.684, and we get the answer, that is 0.688. You can do one more thing, that when you calculate the first one, you can subtract this in 1 and you will get the answer the same. Okay, then the pressure. The pressure P is equal to, that is a P naught of CHCl3 into mole fraction of CHCl3 plus we have P naught of CH2Cl2 and mole fraction of CH2Cl2, and then we have the given values. We know that the P naught CHCl3, that is a chloroform, it is given about 200, and that should be multiplied by the mole fraction. We have 0.312 plus we have the mole, that is the partial pressure of dichloromethane, it is given by around 415 mm of Hg, and that should be multiplied by the mole fraction of the dichloromethane, that is, we have here 0.688. At the end we have the answer, this is 347.9 mm of Hg. This is the total pressure of the solution.